evening to all of you. It gives me immense pleasure to introduce you all to Roger Dannenberg, professor at Carnegie Mellon, at this interactive podcast. Mr. Roger, who is from Pittsburgh, Pennsylvania, United States, is currently exploring the intersection of computation and music, including programming languages, interactive systems, sound synthesis, and music understanding. Mr. Roger is currently focusing on human computer performance, music performance, getting computers to perform with humans. He is also an active classical, jazz, and experimental trumpet player and composer. Recently, Mr. Roger has embarked on two great education projects, that is, Music Prodigy, aiming to help thousands of beginning musicians, and Proxer, aiming to help software developers launch a successful career. So please join me in extending a hearty welcome to Mr. Roger Dannenberg, sir, this incredible crusader of times ahead, as he takes the stage and enlighten us towards interactive performance system. Over to you, sir.
All right. Well, thank you for this invitation. I wasn't really sure what to expect, but I can, let me tell you a little about what I do. I've been working in the area of computer music for over 30 years, and what really brought me into this area, this discipline, was the fact that I was a musician. I am a musician, and also from very early on really enjoyed mathematics and science and engineering, and just building things. And so I pursued formal education in both music and electrical engineering, and then computer science. And everything that I learned in computer science, I would always think about how that might relate to things that I was doing with music. And I was really intrigued by music synthesizers and the ability to sort of mechanically make sound and design sounds, and also the idea of possibly controlling them, to use computers to record and edit and generate musical information. And so this was always really fascinating. And one of the directions I guess strong directions that I've taken has been in interactive performance. And the main reason for that, I think, which is kind of almost funny today, is that when I started, computers were so slow that, for one thing, it was almost impossible to even play a high quality sound on a computer. First of all, no computers had digital to analog converters built in, so there was no sound output, and only research labs had very expensive, complicated, maybe 13, 14-bit digital to analog converters connected to computers, and only the fastest computers could actually read data from disk or tape and convert it to audio so that we could listen to it. And so there were very few opportunities to really work on digital signal processing and sound synthesis with digital computers. However, at the time that I was really learning about computers, microprocessors had come on the market and were developing and were becoming a very important part of computing. And also, microcomputers were sort of paving the way to personal computers. And so even before there were, I would say, interesting, or even halfway powerful personal computers, you could actually buy microprocessors pretty inexpensively, and enough parts to put together, your own little embedded computer. It's something, if you know about Arduino, you might compare, what was possible then to Arduinos now. Although Arduinos are hundreds, maybe thousands of times faster and more memory, but still, it was possible to build small computers. And because the computers did not have a lot of storage and they didn't have real audio, good quality audio input and output, it made more sense to do things in real time, ironically, because if you're doing you don't necessarily need a lot of storage for doing something in real time. You get information comes in, you process it, you send it out immediately. You don't have much time to process it, so you don't have time to read a lot of memory anyway. So you don't need a lot of memory. You basically need a very responsive computer. And then you might think, well, wait, if these computers are slow, how could you do anything? If audio requires all this computation, what good is a slow computer? Well, at the time this was happening, synthesizers and like analog synthesizers were becoming available, and that technology was around. And so, with some care, you could build a computer music system that had a very small microcomputer, maybe an early personal computer, as a real-time controller, and then you could connect that to some kind of real-time special purpose electronics for doing the sound synthesis part. And so that opened up a huge number of opportunities that a lot of people weren't exploring because microcomputers were so new. There wasn't a lot of computer science in the computer music world. And that was an opportunity for me that I took advantage of and explored. And one of the first things that I did, just as an example of what I'm talking about, computers and music and real-time performance, is I thought it would be really interesting to try to get a computer to listen to me as a performer and follow along in a score. So I'm going to play something on my trumpet, let's say, that is written, and there's some written accompaniment to it. And so then the question is, can you get the computer to play an accompaniment while listening to me? And if we could do that, then that would allow me to play trumpet expressively and musically and sort of give control to me as a human performer. And my performance could be sort of expanded and enriched by the computer playing an accompaniment. And this is sort of the opposite of what was happening at the time, which was, and still happens today, that people record accompaniments on as a fixed recording. And maybe there's a click track or a drum track or something that gives you the beat, and the musician is forced to listen to the accompaniment and follow it. Whereas, the musical way to think about things is I'm the human, I'm playing the expressive solo part, so I should be able to be flexible with time and expression and tempo, and let the computer follow me. So it was an early technology that I called computer accompaniment, and I'm still actually working on, just developed a new computer accompaniment system for piano and computer called Accomplice that we're planning to use in a chamber opera this fall. So this is, and many other people are now today still working on accompaniment systems, applying, for example, machine learning to try to make accompaniments more expressive. But I think the most reliable, practical, high performance accompaniment algorithms and approaches were the ones that I developed with some with a student at the time, Josh Block, who became a really important contributor to Java. But anyway, Josh Block and I made these accompaniment algorithms back in around 1985 and 1986. So that's a long time ago. But those are still, I think, the state of the art in computer accompaniment systems. And I could go on and talk about more systems. I'm not sure how much, whether you had other questions or, what should we do here?
Yes, sir. So we do have other questions. So that was truly inspiring to hear from you. So can you please explain how your experiences as a classical jazz, experimental trumpet player, and composer influence at work in computation music?
Oh, sure. So I sometimes think this is my secret weapon for research is that I'm a musician. Um, I've I would never claim that I'm a great musician, but I'm a practicing musician. I've studied trumpet seriously. Uh, I studied for many years and practiced many hours. Practiced every day for decades, and ultimately had a lot of opportunities to perform professionally, and so I think being a musician and thinking about it gives you a chance to think about music all the time, and it helps you to understand, what the real problems are. Because a lot of people, and I see this especially today with lots of young people who are jumping into the sort of digital audio, machine learning world, and their only knowledge of music, or I shouldn't I shouldn't speak for them, but I get the impression that these are mostly people that are kind of casual music listeners. They love pop music and techno and stuff like that, and so they don't really know classical music, either Western classical or Indian classical or anything else, and they don't know about the composition in the 21st century outside of pop music, and there's a lot of thoughts in music and experimental music that are, I think is really important for culture and for music. And so I think having knowledge, beyond being a casual listener has introduced me to a whole set of very interesting problems. And my, computer science background gives me sort of a tool or a way to approach these problems in new ways. And just for one quick example, the computer accompaniment that I talked about was inspired by going to a talk where someone was introducing some hardware for sensing hand gestures, and their idea was they were going to use this hardware sensor to sense a conductor, so they could try to track a conductor's hands and use that to expressively control a computer. And that makes a lot of sense unless you're a musician. Because if you're a musician and you've played in an orchestra with a real live conductor, you know that conductors are not there to give the precise beat and tempo to players. That's just not what, I mean, it would be surprising to anyone that has not played in an orchestra. But if you play in an orchestra, you understand that most of the tempo and the expressive timing comes from listening to each other. And so as soon as I saw this guy talking about conducting an orchestra, I thought, first of all, I know that's never going to work. And second of all, we do this by listening to other musicians. That's what I should do, is build a computer system that listens to another musician, can recognize where they are, and can adapt tempo to synchronize with them. And so that launched the entire world of computer accompaniment. And it was all, inspired by my musical experience, not by technology.
It was truly encouraging, sir. So, can you please elaborate on your initial interest in exploring the intersection of computation and music?
Yeah, well, I think that music is a very logical and mathematical domain, among other things. It's also emotional, expressive, and everything but logical. Um, but I've always been attracted to the logical side of music, and music, logic, and music, and computer science. They're all about manipulating symbols. Even, and you might say, well, yeah, there is symbolic music notation, but there's also audio, and that's what we actually hear. That's true, but actually inside the brain, um, we have categories of. I mean, it's psychologically can be demonstrated through psychological experiments that we have discrete symbolic concepts of music, like beats and pitches and chords, actually form categories, and so they're very, so there is kind of a symbol system behind music that's in our brains, as well as in our notation. So I think music, almost more than any other art form, is just inherently computable and tied to symbolic programming, or tied to symbolic representations that can be approached through programming. And so that just opens up a lot of opportunities, and I think that's what really brought me to tie these things together. When I was studying computer science in school, I thought I was studying trumpet at the same time, and they were just kind of living in two different worlds. And I thought, okay, well, I love playing trumpet. I like to play music. I'm not good enough to make a living. Very few people are. So let's be practical, and I'll just enjoy music, and I'll make money being a computer scientist, working on operating systems or something, and and I'll be really happy. And then after my PhD, I started working on this computer accompaniment and other things, because I just thought, well, now that I have a little time, let's try doing some musical things with computers, just because it would be fun. And then I quickly got sucked into it and was having so much fun that I was thinking about it all the time. And that's where I started doing really the best research. And I realized that the best, that I should really pursue computer music as research in computer science, because that's what I want to do. That's just what I enjoy. That's what I think about all the time. And I was very fortunate to have a lot of encouragement from the powers that be, people like our department head, Nico Haberman, and very forward-thinking leaders like Alan Newell and Herb Simon, and they all just had the attitude that we should just explore computing and learn about computing and do whatever you want, but just do a good job. And so that enabled me to pursue music in a computer science department.
That was a thrilling journey for sure. So, can you please explain us what specific aspect of programming languages, interactive systems, sound synthesis, and music performance do you find most integrating in their relationship to music creation and performance?
Well, that's a great question. I've worked on a lot of different things in my career, and so I don't think I have a great, like a favorite. But I can tell you, the first thing you mentioned was programming languages, and that's something I've really spent a lot of time on, and I think it's interesting. So with the reason, well, the interesting thing about programming languages and music is that music is most importantly about time. And so it's been said often that music is sound organized in time. And so if time is really important, then, well, let's think about what do computer scientists think about time and programming? Well, the standard approach for computer science and time is we want programs to run fast. And so the only question is how long does it take to compute something? And computer scientists talk about complexity, which is, if you want to do something, like the classic example is sorting. If I want to sort a list of numbers, how long does it take? And we say that the complexity is n log n, because as the number of things we want to sort, which is n, grows, the time to sort it also grows, and it doesn't just grow proportional to n, it grows proportional to n log n, if you're really smart about algorithms. And if you do, dumb, naive algorithms, it'll be n squared. And so that's the kind of thing that computer scientists generally think about. It's just, how to make things go fast. Musicians, of course, you're not a better musician if you play the piece faster than everyone else. That would be crazy. Our concept of time is that time is sort of a framework and a structure, and it's a very rich structure, because we talk about time in terms of tempo, and we manipulate tempo. We can speed up and slow down, and be expressive with timing. And they're in modern music or contemporary, 20th, 21st century music. There are, for example, pieces that there's not just one tempo, but multiple tempos and points of synchronization, and lots of experimentation. And so anyway, the point is that time is important. And so how do you talk about time and specify time? And can you, in a programming language where you normally think about semantics of, what does this program compute? In computer music languages, we can think about not only what to compute, but when to compute it. And so this integration of what I call temporal semantics, but the integration of time specification into a formal programming language, leads to all sorts of new programming languages and approaches that relate to functional programming and object-oriented programming. But I've created several new programming languages, all dealing with this question of how to specify time. And so that's been something that I've really enjoyed, and I think has had an impact on the way people think about programming languages for music. So maybe I'll just stop there.
That was great, sir. Sir, can you please enlighten us how different approaches of achieving successful human computer music collaboration, and what are the advantages and disadvantages of it?
Sure. So when you say collaboration, that can be collaboration between humans and computers, and it can be collaboration between humans and humans. So let me just try to talk about all of those. With humans and computers, something that I started doing pretty early, like back in the 80s, was building. I talked about wanting to build these real-time interactive performance systems, and my approach has been as both a composer and a performer. And what I tried to do, or at least I did in a whole series of pieces that I created, was the approach was to give sort of a loose framework for a performance, by writing interactive programs. So these are programs that would listen to me playing trumpet or listen to another player and respond to what they're doing. And my idea was that rather than write music notation and specify what the performer had to do, I would sort of encourage the performer to play in a certain way by creating these interactions. So you create an interaction. Well, so for example, if you wanted a section of music where the emphasis was on rhythmic variation, then you could maybe write an interaction that tried to detect rhythmic patterns and repeat them or vary them, or maybe the system would respond to changes in rhythmic patterns, and then that would encourage the performer to make those changes. And so it's kind of like notation in that you're giving some kind of direction to the performer, but it's very it's not taking a lot of control away from the performer. So it's just encouraging the performer to be creative and work in your terms, as you know, as you're the composer, you're creating the interactions. So the performance is not going to be successful unless they acknowledge those interactions and understand them and work with them more or less in the way that you anticipated as a composer. So that's kind of for me, that's a new form of composition. That's rather than or maybe even a new kind of notation, that rather than notating specific notes, we through programming, we notate interactions. And the reason that's interesting is it allows the performer to improvise, and the performer can bring a lot of, you know, skills on the instrument and specific playing techniques and their own ideas that you might not ever think of as a composer or be able to elicit through notation. And so you kind of get ideally you get the best of both worlds. As a composer, you get to control the overall structure of the piece, but as a performer, you get to, you know, show off and show what you can do as a performer. And so I worked with a lot of pieces in that way, and I think that's a good example of, you know, something that you can do with computers and music that you could never do in traditional music. And I think it's important that, I mean, the goal of computers is not, in my mind, is not to replace or automate this hundreds of years of musical tradition. It's to find, you know, new directions and open up new territory for the future of music. And then let me talk a little about cooperation between humans, because I've been doing some work on network music where people perform over the internet. And there's some very interesting possibilities there. So one, for example, is I ran a concert with, we had 64 musicians all over the world, so including India and the US and Europe and even New Zealand, China, all performing together. And it was just truly inspirational for me, because it's just impossible to really describe the feeling of realizing as you're playing music that you are listening to people everywhere on the planet, and you're all sort of working together to create beauty. And for me, that was just a really great experience, and something that I've been pursuing, continuing to pursue in a way, in that what I'm working on right now is a what I call the global drum circle. So a drum circle is usually a sort of casual gathering of mostly amateur musicians, just playing drums together. and it's a community practice. It doesn't require lots of musical training. Some people are better drummers than others, but almost everybody can keep a beat and play along and join. So it's a very important kind of community building and confidence building and a way to relate to people. And so I had this idea that what if we could have a drum circle running across the internet with thousands of people playing together, and it would run 24 hours a day. And anytime you need to relax and maybe feel some association with other humans, you could get online and play drums together. And so that's there's a lot of interesting problems, including, I mean, the big one is network latency. And the speed of light is really too slow to do the obvious thing. But there are some tricks to allow people to actually synchronize and play together that we're working on. And then there again, we get back to the problem of interaction. You can't just leave it up to people with no direction and nothing to do but play drums, because you have to kind of direct people and give them a purpose and give them some challenges and make them feel accomplishment when they accomplish the coordination that they're trying to achieve. And good in drum circles, there's always a drum circle leader that serves that role. And so we have to kind of figure out how to accomplish the same kind of direction and leadership in a very distributed, automated internet sort of way.
That was truly innovative, sir. Sir, can you please enlighten us on how music education leveraging technology can more effectively empower and inspire students of all age groups and backgrounds?
Yeah. So this is another area that I've worked in, is music education with computers. And I guess the most interesting system that I've created was called the Piano Tutor, and it was a built in the early '90s, which it's kind of hard to imagine, now in the day of YouTube and streaming video. This was a time when computers could barely do any kind of digital video. They were just too slow, and so we were trying to build a multimedia system that incorporated synthesizers, piano keyboard input, music notation, some video display, and integrate all of those and basically simulate what a piano teacher does. But also to give, I guess, like a piano teacher, give interactive feedback to students. So we would present exercises for students to play. They would play the exercises. We would use some of this computer accompaniment technology to follow along and recognize where they are and detect mistakes. And then we would give feedback to the students if they made mistakes and help them practice until they perfect a lesson, and then we move on to the next one. And we also incorporated some automatic lesson selection. So we had around 100 or so very short, small, specific lessons, like, introducing, here's how to place your hand on the piano. Here's an exercise that uses these two fingers. Now we're going to add this finger over here. And, very incrementally, one note, sort of learning one note at a time, one rhythm at a time, one technique at a time. Playing with the right hand, playing with the left hand, playing with the right and left hand together for just one simple piece. And we had 100 of these lessons, and we would automatically select lessons that match the student's skill and their rate of progress, so that if you're very quick, you could actually go through the entire content in a few hours. But if you were a beginning piano player, it would take you months. And in those months, you would accomplish as much learning as typically a year, as a typical student would spend with a human in a year or a year and a half. And so it's very quick and very effective. So that's, I think there is still great promise for music education using computers. Another, the piano tutor and some earlier work led to the creation of smart music, which is used, you mentioned in your nice introduction, it's used by hundreds of thousands of music students today. And then later, I worked I still work with this company, Music Prodigy, which introduced online instruction for guitar playing, and now they're doing a lot of work with, still with guitar and other instruments, using a lot of similar techniques. So I think, the advantage of computers for education is they're tireless. They can listen forever and they never get upset and they never get bored. They're not as expensive as a private tutor, and they can give critical feedback. And in fact, a computer can be much more critical than a human can, because if a human teacher really points out every mistake that a student is making clearly and objectively, it's just devastating. I don't know. I mean, I'm sure many of our listeners have studied music, and we take everything so personally. That if we don't play well, it's this. The teacher can tell us, well, you need to practice this, or they can be polite to us and tell us we need to do some more work, and we get the message. But the teacher can never be as demanding as a computer, because we take it differently when a computer criticizes us. It's more like playing a video game. You get beat over and over and over again, but it doesn't make you sad. It makes you happy, and it makes you work harder. And so, imagine the motivation that people have to conquer a game, a video game, if people applied that to making music and learning musical instruments. It could be a tremendous teaching tool. So, and there's so many other things. As today computers are getting much stronger at listening. We can do some source separation of voices from backgrounds. We can follow pitch. We can follow some rhythm. There's so much that can be done with listening, that and that's the first step in teaching, is you have to be able to listen and understand what someone is performing before you can give feedback. And so all these new things are developing very fast, and I think there's a great future for music education.
That was motivational, sir. So, how do you envision the future of human computer performance, music performance, and what are some of the biggest challenges and opportunities in this field?
Yeah, I think that in the future, we're going to have a lot of live performance with computers. Right now, I mean, of course, we have live performance with computers, but it tends to be either the computer is playing a fixed track of music, which is, kind of boring and doesn't give a lot of expressive opportunity to musicians, or we have digital musical instruments, keyboards and digital effects processors and other other synthesizer sounds, and and those are like musical instruments. But we don't. It's rare especially in popular music, whether it's rock or jazz or folk music or church music. It's rare in those situations to see a sort of autonomous computer as a performer. And a lot of that has to do with the difficulties of reliably, listening to and joining a group that's playing live music. But I think we're making a lot of progress in that direction, and I think there's a lot of opportunity. So in the future, I think that people will be able to get together to play music, and maybe they get together and play and say, hey, we need a drummer. So, you go to your computer and you download a drummer, and maybe you configure it a little bit to tell it what kind of music you want to play, and maybe tell it a little about the music, and then the computer would fill in playing drums or congas, or could be a string section. But I think people will be very creative about integrating autonomous, intelligent performers into live music. And I think it's time now, and there's a real opportunity for kind of a return to live music. I think digital music and computers and networking have sort of turned us away from live music into a culture of recordings and streaming and music as objects that you push a button and you play these objects and listen to them. And I think less and less we're thinking of music as something that requires a live, interactive human performer, and a live audience that's interacting and appreciating that performer. And that kind of relationship is I think has always been part of society, and this idea of recordings is relatively new in the human experience. So maybe computers and this interactive performance and machine learning and AI and computer music is all going to lead us back to a situation where we have more live music, but we're performing music live with robots and with autonomous computers.
That was truly enlightening, sir. Sir, what advices do you have for aspiring musicians and software developers looking to navigate their careers and achieve success?
That's a great question. First of all, I would say the music industry seems like it's really huge, and it seems very like there are many possibilities. I think the reality is it's really a challenge, and the hugeness of the industry is offset by the fact that there are so many players. You look at a company like Amazon or Microsoft, and they are huge. They are economically huge, but the number of people involved is relatively small. Because they're building tools and systems that are each one of which is used by millions of people. Whereas in music, there are tens of millions of songs, and they're all created by people. So there are a million people cranking out songs and not getting paid very much money for it, and also there's a million people buying and selling musical instruments, and so there's but there's just it's a different kind of world than like the kind of high-tech internet companies, because music is much more about content, and it seems to be much more distributed. So given that, if you want to go into the music field, I think the best way is to get really good at computer science and systems building, because those are still the jobs that are hard to fill. And there are lots and lots of musicians without work, but there aren't lots and lots of computer scientists that are really skilled that are looking for work. In fact, there's, in the United States, there are 1 million job openings for IT that are unfilled. That's not the number of jobs. That's the number of jobs extra. That's the jobs left over after everyone has been hired. So, so I think having good, strong skills in computer science is really important. And I also think being a musician and really, studying music and understanding music, not just as someone who likes music and listens to music, but someone who knows some music theory, some music notation, has some real formal study in music. Because if you're working for a company that does music, all of these technologies, I mean, yeah, the fun technologies are either relating to music performance or music composition, and all of those people in that whole culture have real musical expertise. So you need that too. And the final thing I would say is, in spite of all these recommendations, if your true passion is to be a performing musician or a composer, and you're not, and you're doing computer science because you think it's good for you or something, that may be true, and there's probably something for you out there. But I think unless you're really passionate about anything, you're not going to go that far. And so my advice to people is find what you're really passionate about, and as much as you can, pursue that and develop that, because that's what you're thinking about all the time anyway. That's what if you're going to get good at anything, it's going to be what you're passionate about. And I think that's the way to fulfillment and happiness, is to get good at things and do the things that you love.
That was aspiring, sir. So that's it from our side. Thanks a lot for sparing your time and spending your knowledge with us and enlightening and uplifting each and every one of us. Thank you, sir.
All right. Thank you. It's been a pleasure.
Thank you, sir.